Titanoboa, unveiling the mighty giant of the prehistoric world. Welcome, fellow enthusiasts of the ancient world. Today, we embark on a journey back in time, approximately 60 million years, to an era when the Earth was healing from one of its most catastrophic events. Amidst the steamy jungles and swamps of Paleocene Colombia lurked a creature so immense it defied what we believed possible for terrestrial vertebrates. This is Titanoboa cerehonensis, the largest snake ever discovered, a serpent of staggering proportions and a marvel of prehistoric life. Join us as we delve deep into the fascinating history, biology, and the unparalleled legacy of this prehistoric giant. Prepare yourselves for a riveting exploration that's rich with scientific insights and a fresh perspective on a world long lost to time, the discovery of Titanoboa. Our story begins not in the depths of a jungle, but within the bustling Cerrejón coal mines of La Guajira, Colombia, a region renowned for its rich fossil deposits dating back to the Paleocene epoch. In 2009, a multidisciplinary team of paleontologists led by Dr. Jonathan Block of the Florida Museum of Natural History and Dr. Carlos Jaramillo of the Smithsonian Tropical Research Institute unearthed vertebral fossils unlike any they had seen before. These vertebrae were up to 10 centimeters in width, dwarfing those of the largest modern snakes. Comparative morphology analysis indicated these belonged to a snake exceeding 12 meters in length. This discovery was more than an addition to the fossil record. It was a paradigm shift that challenged our understanding of ecological constraints on body size and the evolutionary pathways of reptiles in post-dinosaur eras, the world 60 million years ago. To appreciate Titanoboa's place in history, we must envision the Paleocene world, a planet reshaped by the Cretaceous-Paleogene extinction event that eradicated approximately 75% of Earth's species, including all non-avian dinosaurs. The climate of the Paleocene was markedly warmer and more homogeneous than today. Paleotemperature proxies, such as oxygen isotope ratios in marine sediments, suggest tropical sea surface temperatures reached up to 35 degrees Celsius, 95 degrees Fahrenheit. Atmospheric CO2 concentrations were elevated, estimated between 500 and 1,000 ppm, contributing to a potent greenhouse effect. Cerrejón, situated near the equator, was blanketed by one of the earliest known neotropical rainforests. Palynological studies reveal an abundance of angiosperms, ferns, and primitive palms. The flora suggests high primary productivity and rapid biomass turnover. The fauna was equally impressive. Alongside Titanoboa, there were oversized reptiles like Carbonomus, a freshwater turtle with a 1.72 meter long, 5.6 feet carapace, and diverse crocodiliforms, including Cerejonisuchus and Procerus. The coexistence of such megafauna indicates a thriving ecosystem with complex trophic interactions, perhaps analogous to modern-day ecosystems, but on a grander scale. Physical characteristics of Titanoboa. Estimations place Titanoboa at an average length of 12.8 to 14.3 meters, 42 to 47 feet, with some models suggesting maximum lengths up to 15 meters, 49 feet. Mass estimates range from 1,135 kilograms, 2,500 pounds, to potentially over 1,250 kilograms, 2,156 pounds, based on volumetric calculations derived from cross-sectional area and length. Taxonomically, Titanoboa belongs to the family Boidae, making it a relative of modern boas. Notably, its vertebrae exhibit characteristics typical of boids, such as zygapophyseal articulation facets and neural spine morphology. Biomechanical assessments have been conducted to understand its locomotion and hunting strategies. The robust vertebrae suggest a body adapted for both terrestrial and aquatic environments, but with a preference for the latter due to the reduced gravitational constraints on such a massive body. While we can only hypothesize about its skin coloration, extrapolations based on extant boids suggest potential for disruptive patterns, an adaptation for ambush predation. Scale imprints, if ever found, could reveal microstructures that influence coloration, such as iridophores, which create iridescence. Lifestyle and behavior. Given the environmental conditions, Titanoboa was likely an apex semi-aquatic predator. The hydrodynamic advantages conferred by water facilitated movement despite its massive size. Stable isotope analysis, particularly of carbon and oxygen isotopes in associated fossils, provides insights into the habitat and dietary habits. The data Puy values suggest a diet that included a significant amount of aquatic organisms. Predation strategies were presumably similar to modern constrictors, but on a magnified scale. The snake's musculature would have generated constriction pressures estimated at over 200 psi pounds per square inch, sufficient to induce rapid prey incapacitation. Furthermore, the presence of large fish and crocodilians in the same strata indicates that Titanoboa had access to ample high-calorie prey, supporting its energy requirements. Ectothermy in such a large organism presents unique challenges. The concept of inertial homeothermy or gigantothermy suggests that Titanoboa maintained relatively stable internal temperatures due to its size. Heat retention would have been efficient, but reliance on external temperatures implies vulnerability to climatic fluctuations. Scientific analysis and methods. Quantifying Titanoboa's size involved rigorous scientific methodologies. Researchers utilized allometric scaling laws, employing regression analyses based on measurements from extant serpents. The primary formula used was SVL equals ACLB, where SVL, snout vent length, correlates with centrum length, CL, and A and B are constants derived from regression models of modern boids. Errors and uncertainties were carefully considered. Confidence intervals were established, and multiple specimens were analyzed to account for intraspecies variation. Advanced imaging technologies, such as synchrotron radiation X-ray tomographic microscopy, allowed for detailed visualization of the fossil's internal structures without damage. Interdisciplinary collaboration was key. Paleontologists worked alongside herpetologists, geochemists, and climatologists to integrate data across fields, constructing a comprehensive picture of Titanoboa's biology and environment. Titanoboa's ecological role. In ecological terms, Titanoboa was a keystone species. Its predation likely exerted top-down control on prey populations, influencing the community structure. Mathematical modeling of the ecosystem, using Lotka-Volterra equations adapted for Paleocene conditions, suggests that the presence of an apex predator of Titanoboa's caliber would have stabilized certain population dynamics while suppressing others. Moreover, the snake's existence indicates a high level of ecosystem productivity necessary to sustain such a large carnivore. This productivity could be linked to warm temperatures, high precipitation, and nutrient-rich soils, promoting lush vegetation. Given the diversity of large predators, niche differentiation was crucial. Titanoboa may have primarily consumed aquatic prey, while terrestrial predators focused on different food sources, a phenomenon consistent with the competitive exclusion principle. The extinction of Titanoboa. The extinction of Titanoboa aligns with significant climatic shifts at the Paleocene-Eocene thermal maximum, PETM, approximately 55.5 million years ago. Paradoxically, this period experienced a rapid temperature spike, but subsequent cooling and aridification altered habitats dramatically. Isochronal stratigraphic analysis reveals shifts in sediment composition indicative of changing environments, from swampy forests to more open, drier regions. Lower global temperatures reduced the habitable range for such large ectotherms. Additionally, changes in sea levels and orogeny events could have fragmented the habitat, leading to population bottlenecks. The emergence and diversification of mammals introduced new competitors and altered prey dynamics. While not necessarily direct causes, these factors contributed to the complex web of ecological pressures leading to Titanoboa's extinction. Modern significance and legacy. The study of Titanoboa extends beyond paleontological interest. It has profound implications for understanding climate change. By examining the relationship between body size and ectotherms and ambient temperatures, researchers can refine models of paleoclimate conditions, a field known as paleobiothermometry. This contributes to our understanding of climate ecosystem feedback mechanisms, potentially offering analogs for current global warming scenarios. From an evolutionary perspective, Titanoboa provides critical data on snake evolution post-KPG extinction. Its characteristics bridge gaps between Cretaceous and modern species, shedding light on morphological trends and adaptive responses. Public interest in Titanoboa has been instrumental in promoting science education. Museums featuring Titanoboa exhibits report increased visitor engagement, and documentaries bring complex scientific concepts to a broader audience. Fascinating facts about Titanoboa. To satiate your curiosity, here are some remarkable facts about Titanoboa. Largest terrestrial vertebrate predator post-dinosaurs. Titanoboa wasn't just the largest snake, it was among the largest terrestrial vertebrate predators during the Paleocene, rivaled only by certain species of crocodilians. Implications for serpent phylogeny. The snake's features suggest a more diverse and widespread distribution of boyd snakes in the Paleocene, prompting reevaluation of phylogenetic trees and biogeographic histories. Potential for endothermic tendencies. While snakes are ectothermic, some researchers speculate that Titanoboa may have exhibited partial endothermic traits or metabolic adaptations to sustain its massive size, a hypothesis requiring further evidence but intriguing nonetheless. Clues from coprolites. Fossilized feces or coprolites, potentially attributed to Titanoboa, have provided insights into its diet, including remains of large fish and crocodiliforms, offering a direct window into its feeding habits. Our exploration of Titanoboa sarahanensis is more than a tale of a gigantic snake. It's a narrative about Earth's resilience, the adaptability of life, and the intricate interplay between climate and biology. Understanding Titanoboa helps us appreciate the complexities of ecosystems and the factors that shape them over geological timescales. As we face our own era of climate change, the lessons from Titanoboa's time are increasingly pertinent. They remind us that shifts in climate can have profound and lasting impacts on biodiversity. Let the story of Titanoboa inspire us to deepen our commitment to studying and preserving the natural world, both for its intrinsic value and the insights it offers into our own species' future.